Everyone, today we are going to talk about buffers. But to successfully understand buffers, you need to remember what Bronsted-Lowry acid-base conjugate pairs are. At this point in your chemistry career, you should already have learned this in class, but if you need a little refresher, we're going to do a quick review. Now, the definition of a Bronsted-Lowry acid, which I'm going to abbreviate BLA, is something that produces a proton. Something that produces a proton, also known as H+. An example of this might be carbonic acid, which is H2CO3. A Bronsted-Lowry base is something that accepts an H+. So, accepts H+. And that would be something like HCO3 minus. For something to be an acid-base conjugate pair, you're basically looking for one hydrogen difference between the two. If it can donate a hydrogen and accept it, then it can be a Bronsted-Lowry acid-base pair. So H2CO3 compared to HCO3 minus. These are conjugate pairs of each other. The acid is the one that is more positive, and the base is the one that is more negative. If you look here, you have two hydrogens, and here you have one. Now, a common mistake is to have something like CO3 minus 2. And I think that these two guys are conjugate pairs of each other. But in order for them to be conjugate pairs, you only need to have a one hydrogen difference. If there's a 2 difference, then it doesn't work. Those are not conjugate pairs of each other. And that is going to be a big thing when working with buffers. For buffers, you need conjugate pairs of weak acids and bases. We cannot have strong acids with this, so no strong acids. We need the reaction to be able to go both forward and backwards. In weak acids and bases, let us do that. Now, the purpose of a buffer is to maintain the pH of a system. Maintain pH, and that can be in a generic solution, such as you'd use for maybe pharmaceutical products or personal care, or in biological systems. Your blood actually has a buffer in it to keep it from becoming too acidic or too bases. pH and buffers are super important for biological sciences, so this is a great thing to learn. And the main equation that goes with buffers is the Henderson-Hasselbalch equation. Henderson-Hasselbalch. And if you forget, there is a really great way to remember it. The equation is pH equals your pKa plus the log of your base over the original concentration of your acid. And the expression that goes with this is hippie kids always drop acid. Hippie goes with pH, kids go with pKa, and drops acid is putting your acid at the bottom of your log. And that is just a fantastic way to memorize this equation. Now, using the equation above and the knowledge that the pKa is 1.85, I want you to find the pH of a buffer containing 7.2 times 10 to the negative 4 molarity H2SO3 and 4.7 times 10 to the negative 3 molarity of HSO3 at equilibrium. Now I want you to pause the video and give it a go. Okay, hopefully you've paused the video, given it a try. Now the first thing we're going to do is write down our Henderson-Hasselbalch equation with all the information inputted into it. So we have our pH, which is what we're trying to find, equals our pKa, which is 1.85, plus the log of A minus. And if you look here, look for the one that is more negative. This is HSO3. So that means 4.7 times 10 to the negative 3 goes up top, and the acid, the more positive one, goes on bottom. 7.2 times 10 to the negative 4. Now if you put in the log of this, you should get pH equals 1.85 plus about 0.81. And if you add these two together, you should get pH equals 2.66. And that is how you find the pH of a buffer. Now, I want you guys to try one more problem. What ratio of conjugate base to conjugate acid is needed to make a pH 7 buffer from hypochlorous acid? It's given that the pKa is about 7.4. If you ever have a problem like this and you don't know the pKa, go look it up on the internet. That is a perfectly acceptable option. And use this equation. Pause it, give it a go, and let's see if you're right. The first thing you're going to do is write down what we know. So we know we want a pH of 7, and that equals our pKa, 7.4, plus the log of base to acid, so A minus over HA. The next thing you're going to do is get this side alone. So you're going to subtract 7.4 from 7. And that gives you negative 0.4 equals log of A minus to HA. To undo the log, you're going to have 10 to the power of negative 0.4. And you're going to do that to both sides, and that will give you your ratio of A minus to HA. And if you write it over on this side, because I'm running out of room, 10 to the power of negative 0.4 is, if you round it, 0.4 equals A minus over HA. Now we're asked what ratio is needed. So here you can use the rule of anything divided by itself, or anything divided by 1 is itself. So 0.4 divided by 1 equals 0.4. So using this, we know that our A minus, our base, is going to have a concentration of 0.4 molarity, and our acid, HA, is going to have a concentration of 1 molarity. Now there are 4 main points I want you to take home from this video. The first one is you need conjugate acid-base pairs. Acid-base pairs. They have to be conjugate acid-base pairs of each other. If you don't have that, you're not going to have a good time. Next one is no strong acids or bases. These make terrible buffers and are just truly not good. It is a common mistake to have a conjugate acid-base pair of a strong acid and have that on exam, but that doesn't actually work because they're strong. You need weak. Need weak acid and bases. Third point, the Henderson-Hasselbalch equation. pH equals pKa plus the log of base to acid. Understanding each part of this equation and how it works together will give you a fantastic understanding of buffers. And the last one is picking a buffer. You want a buffer that is equal to your pH plus or minus 1. So if you're looking for a buffer, look for its pKa that is equal to the pH of what you're trying to work with, plus or minus like a value of 1. And this will give you a good pKa to work with the buffer. And that is all I have to say on buffers. I hope this video helped, and I will see you in class.